Okay, we continue here with the calculation of volumes of revolution, right? So we will begin with the first one. The first one is the volume of revolution generated when an ellipse rotates around the x-axis. The shape of an ellipse is like this. So let's say that the horizontal axis, this A, is larger than B. Doesn't matter, right? It's just for drawing purposes. It could be the other way around. Doesn't matter, right? So we have to rotate this, and when we rotate this, of course, we have a solid which is called an ellipsoid. Ellipsoid of revolution. Okay. The equation of an ellipsoid is like this. So an ellipsoid is a solid, right, in which the three axes may be different. Okay. C squared equal to 1. But in the case that we have here, right, the B and C are the same. B is equal to Z. And then we have a solid of revolution, right? The for a given x, this is the coordinate x, so we make a section at a fixed x. What it generates, the cross section here, is a circumference, right? Because if we fix this and put it here, then what we have is we have y squared plus z squared equal to b squared. Remember, b and c are the same, multiplied by 1 minus x squared divided by a squared. Okay, this is a number, right? And this number is the square of the radius of this circumference. So this circumference is the cross section at a fixed x, right, of this solid of revolution. Okay, so we want to calculate the volume of that, and for that we just need to calculate what is the shape of this function here, and we obtain that from the equation of the ellipse. So if we eliminate y, what we have is plus or minus b times the square root of 1 minus x squared divided by a squared. There's plus and minus because there are two pieces of the ellipse, the positive one and the negative one. We just need one of them, so we stick to the positive one, right? Okay, so that is the function f that we're going to use to calculate the volume of revolution of this. We just want to calculate the formula for this, which is the integral from minus a to a of b squared times 1 minus x squared divided by a squared dx. Okay, the square of the function f. This is a constant, comes out, all right, and then we have a polynomial, just a polynomial. Actually, we can multiply by 2, right, because it's symmetric and the function is even. We can multiply by 2 and integrate only half the interval. This is just like calculating half the volume, right, only the positive side on the positive bit, and multiply by 2. Okay, so that would be equal to this, a squared dx. And the primitive of this is straightforward. It's just x minus x cubed over 3a squared. I have to substitute on 0 and a. Okay, for 0 this function is 0, so we have to substitute by a, and by a we have 2 pi b squared, and we have b, and then we have a, and then we have a cubed over 3a squared. We can cancel the cube with the a squared here, and then we have a third, and here we have a, so that's 2/3 of a, so the formula is 4 pi divided by 3 b squared times a. And if you look at this carefully, you realize that there is a strong connection between this and the formula of the volume of a sphere. Actually, if a is equal to b, then what we have is a circumference of radius a, and that would be the volume of the sphere that it generates rotating around the x-axis, and this volume would be 4 pi cube a 4 pi over 3 a cube, which is exactly the volume of a sphere. So this is how it generalizes the formula for the volume of one of these ellipsoids here. The second question that we're going to answer is this the revolution of the same shape, but this time around the y-axis. Okay, so we're going to rotate this around the y-axis. Okay. All right. So what we're going to do is to do the same calculation, right? So we have here, we have this piece of the ellipse, which is the one that is going to rotate and generate that. And then, well, of course, we have here a similar one. So what we're going to do is to consider just the one on top and multiply by 2 the result, right? And we rotate this around the y-axis and it generates another ellipsoid of revolution. But it's different from this one, right? In this one, the cross-section perpendicular to the x-axis is a circumference. In this one, the cross-section perpendicular to the y-axis is the one that is a circumference, right? Okay, so if you go to the formula of the ellipsoid, in this case, is A and B, what are the same, right? Okay, so let's see how to calculate this. The formula, remember, is equal to 2 pi the integral of from, okay, we have to multiply, is 2 pi, well, let me just write the formula first, and then we'll, so this is the formula for general function f, right? In our case, well, this gives, of course, the volume generated by this region when it rotates. So we have to multiply by 2 in our case because we have the same shape here and generates exactly the same volume as the curve up here. Okay, so the volume in our case is going to be 4 pi. Now the interval is of course 0 to a, right? So interval goes from 0 to a. Then we have x, and the function that we have here is exactly the same function that we have calculated here for the other ellipse, right? It's exactly the same function, only that we're considering half the interval, right? So this is b times the square root of 1 minus x squared divided by a squared dx. Okay, so now we have to integrate this. Let's take out all the constants. In this case, these are the constants. Then we have 0 to a, then we have x here, and here we have the square root of this. Okay, now look at this function that we have here. The derivative of this function here, what is inside the square root, is minus 2x over a squared. There is an x here, and we already have an x here. The rest are constants, so we can compensate by multiplying and dividing by the appropriate constant. So if we multiply by minus a squared over 2, and here by minus 2 over a squared, right? Then what we have, let me just put this as a power. So what we have is this. We have a function to a certain power and multiply by the derivative of that function. Okay. Okay, this is an immediate integral. It's an immediate primitive. The primitive of this is 1 minus x squared over a squared 3/2 divided by 3/2, which is multiplied by 2/3. All right, so this is the primitive of that. So all I have to do is to substitute this primitive now. So I have, well, 4 pi b multiplied by minus a squared over 2, and then 2 over 3, and then 1 minus x squared over a squared to the power 3/2 between 0 and a. All right. Let's see. Well, there is a 2 here, there is a 2 here, goes away, so we have 4 pi divided by 3 b and a squared. Okay, and now we have for a, this is 0, right? Because you put a here, then this is 1, 1 minus 1 is 0. So it has to subtract the value of this at 0, and at 0 this is just 1. We have to subtract, but there's a minus here, so the product is a plus, and so you just have to multiply by 1. So you get the formula for the volume, which is 4 pi over 3 BA squared, which is pretty much the same formula that we have obtained before, but A and B are here interchanged. The reason being that in one case we are generating a solid of revolution rotating around the x-axis, and so in this formula for the ellipsoid, these two radius are the same, and in the other case it is these two radius that are the same, right? And the other one is B. Well, let's say this and these are the same, A and C are the same, and the other one is B. Okay, so it's very similar, right? And finally, the last volume of revolution that we have to calculate is this one here, which is the following. It's a different story, because what we have here is a solid whose base is this ellipse, right? And whose sections perpendicular to the y-axis are isosceles triangles of height 2. So that's a different story. It's like a tent, what we have to calculate now, right? It's the volume of a tent. So the idea is, let's try to figure out what this is like. So let's try to plot these in the x, y, and z axis. So this is x, this is y, and this is z. Okay, in the plane xy, this is going to be an ellipse, so it's pretty much like this. All right. So this section here is B minus B. This is A. This is minus A, right? And then the cross section perpendicular to the which one? The x-axis. Well, actually, let me plot it in a different way, because it's going to be perhaps more easy to see. I'm going to exchange the two axes. This is going to be the x-axis. This is going to be the y-axis. Okay, so this is going to be A. This is going to be minus A. This is going to be B. And this point here is going to be minus B, right? And now what it says is, if you make a cross section, right? Let's say here, perpendicular to this. So this should be parallel to the y. Try to plot it parallel to make it absolutely clear. What you have is an isosceles triangle, right, of height 2. Okay, so this height here is 2. So every cross section here is an isosceles triangle. Again, this cross section should be parallel, so like this. Is an isosceles triangle of the same height. All of them have height 2. So the one that you have here is just a straight line, by the way. Okay, and you continue this way, so you have this isosceles triangle here. Okay, and you can continue like this, so you have this one here. Okay, this one here. Okay, I hope you can figure out what this look like, right? So this is the top, and it's all of them at height equal to 2. Well, the important thing about this is that we know the cross section, and if we know the cross section, we can calculate everything, right? So it is the cross section at at a given point of x, right? X goes from minus A to A, because this is the cross section of this ellipse, well, this solid, right? So we need to calculate how much is this length. So this length is this section, so the length of y's, right, for a given x. We have the formula x squared over a squared plus y squared over b squared equal to 1, which describes what is the what are the points on the ellipse, like this, right? So if we want to calculate what are these points, to calculate this distance, all we have to do is to eliminate this for a fixed x. Okay, so we have, as we had before, b plus minus b, the square root of this, x squared over a squared. Okay, these are these 2 points. So the distance between these 2 points, so let's say the increment of this y here the base of the triangle, will be the plus minus the minus is 2 times b, the square root of 1 minus x squared over a squared. So that is this length here. Now we have to multiply it by 2, which is the height of the triangle, and divide by 2, because it's a triangle. So the area of the triangle at a certain, well, let me call it with a capital letter to distinguish from this a here. So the area of the triangle at a certain, I don't know why I wrote z, said x, at a certain cross-section x is given by, as I said, 1/2 of 2 times this number here, so this is just equal to this over a squared. And now all we have to do is to integrate this area. To calculate the volume, we have to integrate this cross-section along the whole interval, right? So this is Pappus theorem, okay? So we substitute that, and we get 2b times the integral from minus a to a of the square root of 1 minus x squared divided by a squared dx. Okay, this is a. This is an even function. The interval is symmetric, so we have twice half the integral. So this, right? Multiply by 2 and reduce the interval to only half of it, right? Okay, and to calculate this, we can make a change of variable. The change of variable is we can take x equal to a times the sine of phi, right? And dx is a cosine of phi d phi. All right, so we have this constant a, so we have 4ab here. Okay, then we have the integral from, for x equal to 0, the sign is 0. For x equal to a, the sign has to be 1, so it's by half the angle, right? Then we substitute here, and what we have is the square root of 1 minus sine squared of phi, okay, because we divide by a, and this is the cosine of phi, so we have a cosine because of this square root, and another cosine from here, so we have the cosine square of phi d phi. That is equal to 4ab, and remember we can actually 2 times this, remember 2 times the cosine square of phi is equal to 1 plus the cosine of 2 phi, and that is exactly what we're going to write there. So it's the integral from 0 to pi half of 1 plus the cosine of 2 phi d phi. All right, okay, then we have 2ab. The first integral is just pi half. The second integral, well, the primitive of this is just 1/2 of the sine of 2 phi between 0 and pi half, which is just 0. Okay, because the sine of 0 is 0, and the sine of pi half, 2 pi half is sine of pi, which is 0, right? Then we have pi a b, and that is the volume of this solid that we have figured out here.